All right. So over the weekend, you guys should have done or worked on this homework 1, right? We'll start here with questions. Does anyone have questions from homework 1? Joey?
You want us you don't have to drop into a Dropbox, right?
Just put it in OneNote, just like last semester. Yep. Good. Whatever. You can live down there. Yes. Go ahead, sir. Hi.
Can you do either 2 or 4?
Sure. Okay. I realized that I hadn't done my attendance, so I'm just gonna stall for a second while I get that in. Has anyone seen Lily today? No. How about Jack? Couts.
I've not seen Jack House.
Okay. And then everybody over there, right? How about Janet? Have we seen Janet?
Joey, you should just Joey, you should just want 8 out of clubs.
Okay. And it's Gabby, right? You said 2 or 4? Does anyone have a preference on 2 or 4? Okay. Nobody has a preference? Well, I guess we'll just do 2 for numerical purposes, that it comes first. So f plus g of x. Basically, all we're doing there is we're going to take f of x and then add to it g of x. And then we're just going to look for some like terms to combine. So the only x to the 5ths I see are there. And then I can take 5x to the 4th and 2x to the 4th. That's 7x to the 4th. And then these are my only x cubed. So I'll just transfer that down. This is my only x squared. Transfer that down. I have negative 3x and positive 1x. That'll give me negative 2x. Then I have 7 and negative 3, which will be positive 4. That's it. Gabster, what do you think?
Yeah, I was just
It might have been just the notation that I used there, right? That was just me trying to not have to type all those things a bunch of times.
Is it 4x or just 4? I wrote down 4x.
Here at the end?
Yeah.
Should just be 4 because it was negative 3 and positive 7. No x's on any of those.
Do you know anything like technical with that?
So this x right here is not being multiplied by x. That's function notation. So like, you know how we write like f of x equals or whatever? That's that x. So it's not being multiplied by x. Is that?
Yeah.
Okay. Okay. Other questions from homeworks? Happy to do more. Again, this is the place where we get most of our feedback on what we've done, right? We're not going to go through every single problem on every single homework. So if you're not sure about something or you tried something, you're like, yo, I don't know if I did that right, this is the time to ask. Typically, we start every class with questions from homeworks. So this is a good time to get your clarification if you're not sure about it. Okay. So today, then, we're going to start talking about factoring polynomials. And we're actually going to spend several days kind of on this content. So we'll take a couple of days here and really we're going to break this content even into two parts. So we'll spend some time here the first day, or the first part we'll take a couple of days kind of talking about this topic. And then we'll kind of move away from it for a minute and then circle back to it a little bit later and take several days coming back to this. So this first part of factoring polynomials, what we're really going to be doing is we're going to be using the tools that we developed in last semester to factor polynomials. And we'll spend some time working with those tools. But that's not going to be able to, those tools won't allow us to factor everything we need to. So we are going to expand on those tools later on in this chapter as well. So we'll initially here, though, these tools are going to be using the same kind of techniques that we developed last semester. So what I'm going to do is I'm going to write like a flow chart that'll kind of describe like how we're going, like the work we're going to do and the order that we're going to do things. So my suggestion to you might be that you might want to, if you're taking notes on paper, to turn your paper like landscape style so that it's wider, because the flow chart gets wide and not necessarily super deep, but it gets kind of wide. So if you're writing on a sheet of paper, it might be easier if you write it sideways. And if you're on your tablet, obviously, like using OneNote, like start kind of in the middle of your OneNote page so you have some space to kind of extend either direction. Okay. So our starting point is some polynomial. The first thing we're going to do is check for a greatest common factor. So I abbreviate that as GCF. So for example, what do I mean by a greatest common factor? Say you have the polynomial 2x squared plus 4x plus 6. That has a greatest common factor of 2 because each of the terms of that polynomial are divisible by 2, right? And then we're going to look at the number of terms. And there's 3 situations that we're going to deal with. So that's if we have 2 terms, if we have 3 terms, and if we have 4 terms. So make sure you make those pretty wide apart because there's going to be a lot of stuff underneath that. And I'm going to work just from right to left. So we'll start with the 4 terms first. So for the 4-term polynomial, the first thing we're going to do is check to see if it's factorable by grouping. If it is, we're going to factor by grouping, and then we have to check each factor in the two terms branch. If it's not factorable by grouping, then we stop. We don't have any, currently we would not have a technique to use in that situation. We will have some other stuff we can try later on. But for the time being, we're out of things to try. So again, the idea here is we're going to take the things that we already know how to use and already know how to do and factor as much stuff as we can without having to create any new processes. We're just going to take things that we already kind of know and like combine them together maybe in a slightly different way or a slightly more general way to do these new kinds of problems. The second chunk of talking about factoring of polynomials will introduce some new concepts and some new techniques that we can use to factor things that we couldn't by using this list. Yes?
What is it? The box of
Each factor in two terms. All right. So under three terms, the first thing we're going to do is check to see if it's in the quadratic form. I'll define what that means here in a few minutes. It doesn't mean that it's quadratic, but it's kind of similar to that. If it's not in the quadratic form, there's nothing more we can do with it with our existing technique, so we would stop. If it is in the quadratic form, then we want to check to see if the leading coefficient is 1. I abbreviated leading coefficient as LC. If its leading coefficient is 1, we can use our shortcut factoring, or we can try to use our shortcut factoring, and that might be possible or it might not. If it is not possible, we're done. We don't have anything else we can try. If it is possible, then we'll do that shortcut factoring and then check each factor in the two terms branch. And if the leading coefficient wasn't 1, we have to do the full version factoring. If that full version factoring doesn't work, we have to stop. There's nothing else we can try. If it does work, then again, we have to check each factor in the two terms branch. Again, what we're developing here is just like a flow chart to kind of make sure that we don't miss anything when we start doing these factoring problems. So we're just kind of finding a way to describe what the procedures are that we're doing and the order in which we want to do things to help kind of optimize this for you guys so it is as easy as possible or as well organized as possible. And this graphical way of doing things, I think, is often helpful for students, where you can kind of treat it like a map. We're like, okay, next thing I do is this, and if the answer is yes or no, then I do something, and then I do this, and I do this until I get to a stop. Yes? Full version factor? You're welcome. Okay. And the last thing we have to do is fill in the two-term branch then, right? So let's go over there. So the first thing we'd want to check is it a difference of two squares? I abbreviated difference of two squares as DOTS, dots. If the answer is yes, then we'll check each factor in the two terms branch. The answer is no, then we'd need to check, is it a sum of two cubes or a difference of two cubes? Again, I abbreviated those. SOTC for sum of two cubes, and DOTC for difference of two cubes. In just a moment, I'll explain to you what those mean, or what that means, as those are new concepts or new terminology for us. And if it is a sum or difference of two cubes, then we factor it using that method. And then we want to check each factor okay. So, zooming out, we have this big flow chart here, which again looks pretty intimidating, but is not so bad once you kind of get the hang of using it. You'll find that it's kind of like the same steps over and over and over again. Where basically you do some factoring and then you check the factors to see if you can factor them more over and over and over again until you can't factor anything else. I used a bunch of abbreviations or some new terminology here. So just on the side, I'm going to go ahead and define what some of these abbreviations and some of this extra terminology is, so that if you're going to look at this thing, you're not thinking like, oh, what the heck was that again? Or he said this, but I didn't write it down, or any of those things. So GCF was, again, greatest common factor. So if we have something like 2x to the third minus 4x squared plus 10x, you'd notice there's a 2x in common with everything. So you could factor that 2x off, and this 2x would be in this case, the greatest common factor. Everybody's okay with that idea? The quadratic form is things that are of the form ax to the 2n plus, bx to the n plus c. So an example might be something like x to the fourth plus 5x squared plus 4. Basically, all we're looking for, if you're looking at something in the quadratic form, is the big exponent should be 2 times the other exponent, and then the last piece should be a constant. So there should be no variable attached to the last part. That's what we mean if something's in the quadratic form. So if the exponent was to the 6th, and then to the 3rd, and then you had a constant, that would be in the quadratic form, right? Is everybody's okay with that idea? So again, pretty straightforward, almost basic, almost exactly what we mean by quadratic, but it's a little bit broader, right? It includes all the quadratics from first semester, and then some of these other things that are polynomials that are going to act a lot like a quadratic when it comes down to factoring. Let's see, what else was on there? So DOTS stood for the difference of two squares, and I'm writing this a little bit more generally than we would have in the section on quadratics. Because technically speaking, if I had like x to the fourth minus y to the fourth, that still should count as a difference of two squares, as long as both of the exponents are the same even exponent. And we'll do some examples with that here in a moment when we actually do some factoring examples. But this is really just the more general version of a squared minus b squared equals a plus b times a minus b, right? That we used a lot last semester and we should be pretty comfortable with. Well, let's do difference of two cubes first. And similarly then, sum of two cubes. Is there. So again, just another factoring pattern. These are two new factoring patterns that we haven't studied before, and that's okay. They're not too hard to use, right? You just have to know the factoring pattern or use the correct factoring pattern there. But other than being a little bit longer than the difference of two squares, it's not really much harder to use than the difference of two squares. It's just kind of like a formula. And I think I said LC for leading coefficient. I think I used that abbreviation, but we should know what that means, right? That was a vocab from last time. Was there anything else on that flow chart that needed some extra explanation or a note to remind us what that meant? Or that was new? I think those were all the things, weren't they? If anything comes up, let me know. If we see something and you're like, oh, I'm not sure what that was or whatever, like holler at me and we'll go back and add it to the list or whatever there. Are we ready to start examples? I still see some people writing. I don't want to rush you through it if you're still kind of getting things down. We're okay, though? Okay. So we'll do a bunch of examples now, but this is all the content that we're going to do for today is just kind of defining this factoring diagram, this flow chart, and adding on this little pieces of vocab and formulas. And then we're just going to do some examples using all of this stuff. And that's going to be plenty for today. That was a lot of material kind of reorganized, even if a lot of it is repeated, things that we're should be familiar with. It's reorganized, and we added some more vocab, and it's a lot. So let's kind of do some examples, and I'll point out kind of how we're using this flow chart, and I'll actually walk through the flow chart, like pointing to where we're at here in the beginning. And as we get further on with more examples, I'll stop referring so much and just doing it. I'll just say it aloud, kind of where we're at rather than physically pointing to it. But we'll do that in the beginning here. So we're starting with our polynomial that we want to factor. The first thing we do is look for a greatest common factor. So our polynomial is 3x to the fourth minus 54. Is there a greatest common factor there? Well, the only possible greatest common factor can be the number 3, right? Since the second term doesn't have any variables, and the first term is only divisible by 3, does 3 divide 54? Yes. And again, the dividing by 3s is an easy check to make, because if you add up the digits of that number, and that's divisible by 3, then the number is divisible by 3. So for example, 54, the digits are 5 plus 4, that's 9. Since 9 is divisible by 3, I know 54 is divisible by 3. That only works for 3's, by the way. But it's a nice fact to know. It's useful quite often. So 54 divided by 3 is 16. So that's going to be x to the fourth minus 16. So we passed through the greatest common factor. Now we're going to look at the number of terms. In this problem, we have 2 terms, right? We have x to the fourth, and then we have the minus 16. So is that a difference of 2 squares? Yes, right? Because I can rewrite x to the fourth as x squared squared. And I can write 16 as 4 squared. Everybody agree with that? So we can now factor that using our difference of 2 squares to get x squared minus 4 and x squared plus 4. Everybody okay to there? So now we need to check each of those factors back through the two terms stretch. So our first factor was x squared minus 4. Is that a difference of two squares? Yes. That's an easy one, right? It was just like it was in first semester. That's just going to turn into x minus 2, x plus 2. Now we need to check x squared plus 4. Is that a difference of two squares? Be careful. Is it a difference of two squares? No, right? It is a sum. That is not factorable. And then we just need to go back and check the x minus 2 and x plus 2 to see if those are factorable. Neither of them are, because they're both linear terms, right? As soon as you see a linear term, you know is immediately it's not factorable anymore. So this would be our final answer. So far, so good? Okay. So very similar to the quadratic factoring that we did last semester, right? It just got kind of more layers to it. Because every time you do a factoring, you have to check your answer to see if you can factor that anymore. Plus. Squared. Okay. So let's say we have x to the fourth plus 3x squared minus 28. So again, first thing we check for is the greatest common factor. Is there a greatest common factor here? No, right? Should be easy to tell because the first term contains only x's, and the second or the last term contains no x's, so no greatest common factor because there's nothing in common with those two. Okay? So then we look at the number of terms. How many terms do we have here? 3 terms. Okay. In the 3 terms, the first thing we look to see is it in the quadratic form? Is this in the quadratic form? Well, to do that, I'm going to look at the exponents. The biggest exponent is twice the middle exponent, and the last number is a constant, so that is in the quadratic form. Everybody's okay here? The next thing we check is the leading coefficient. What's the leading coefficient in this case? Remember, the coefficient is the number in front of the biggest degree term. In this case, the leading coefficient is 1. So we should be able to do this with the shortcut factor. So we're looking for 2 numbers then that would multiply to give us negative 28 and add to give us positive 3. What are those 2 numbers? 7 and negative 4. Very good. So just as an aside, if we had x squared plus 3x minus 28, we just write this as x plus 7, x minus 4, right? Here, though, we have x to the fourth plus 3x squared minus 28. So this is going to be x squared plus 7 and x squared minus 4. Basically, the rule of thumb is whatever that middle exponent is will be the exponent in your factors, which was just the same case here, right? So far, so good. Now we need to check each of those factors to see if they're factorable. So let's do the x squared plus 7. We go over to the 2-term stretch. Is x squared plus 7 a difference of 2 squares? No. Then we check, okay, is it a sum or difference of 2 cubes? Definitely can't be because it's an x squared, right? It needs to be at least, the exponent needs to be a multiple of 3 for it to be a difference of cubes. So that one's done. Now let's check the x squared minus 4. Is that a difference of 2 squares? Yes, right? So we can factor that a little bit more. X squared minus 4 turns into x minus 2, x plus 2. Everybody's okay there? And then we should check each one of those factors to see if they're factorable, but because since they're both linear, we don't have to do anything, right? So that's done. Oh, excuse me. All right. So sleepy. All right, next up. Okay, so we have x to the fourth minus 5x, or sorry, plus 5x to the third minus 27x minus 35, or 135. Okay, where do we start? Greatest common factor. Is there one? No. Okay, next thing we go to is the number of terms. In this case, how many terms do we have? 4. So what we need to do is try to factor this by grouping. So when we factor this by grouping, we group the first 2 terms together, and then we group everything else together, or in our case, the second 2 terms together. And then we pull a greatest common factor from each of those 2 terms. So from the first term, what's the greatest common factor between x to the fourth and 5x to the third? X to the third. So when I factor an x to the third off, I'm left with x plus 5. Then I go to the second term, and we look for a greatest the second piece, we look for a greatest common factor between negative 27x and negative 35. Well, clearly it's negative, right? Since they're both negative. We can at least take a negative 1 out. Can we do better than that? Well, they're both divisible by 3, right? 27, 2 plus 7 is 9. That's divisible by 3. 1 plus 3 plus 5 is 9. That's divisible by 3. So they could both take a 3 out. Is that all, though? So what are the only divisors of 27? 3, 9, and 27, right? So let's just check to see if 135 is divisible by each of those. And I would start with the biggest one first, because if it's divisible by 27, then we're done, right? So is 135 divisible by 27? Yes. And the quotient when we get that is 5. 135 divided by 27 is just 5. So to check to see whether it's factorable by grouping, that part has to be the same. Since it's the same, it is factorable by grouping, and we can continue. If it wasn't, we would just stop, and whatever wherever we're at before, in this case, the original problem would be as good as we could do. So we can take out the x plus 5, and then that leaves us with x cubed minus 27. And now we need to check each one of these factors to see what we can do with them. The x plus 5 clearly is not factorable, right? Because it's a linear term. The x cubed minus 27, we'll go through the 2-term branch. Is it a difference of 2 squares? Definitely not, right? Because the exponent is odd. Can't be a difference of 2 squares if your exponent is odd. Is it a sum or difference of 2 cubes? Yes, okay. So we can definitely write x cubed as something cubed. How do we write 27 as something cubed? Well, 9 times 3 is 27, but that's not the, multiplying by 3 isn't the same thing as cubed. Hi. Welcome. But what is 9? 9 is 3 times 3, right? So 3 times 3 times 3 is 27. So 3 cubed is 27. Everybody agree with that? Okay. So my difference of two cubes factoring pattern, I'm just going to write down here on the side so that you guys don't have to go back and flip all your pages back and forth looking for it. So if I use this, I would say that the A is x and the B is 3. Do we agree with that part? If we look at the form, that's how I got those pieces. So now I'm just going to plug that into the other side. So the x plus 5 didn't change, but A minus B is going to be x minus 3. A squared is x squared. A times B is 3x. And B squared is 3 squared, so 9. Are we okay with how I plugged that into the factoring pattern? Again, not much different than the difference of two squares factoring pattern, other than like it's a different pattern, right? But we still kind of approach it the same way, except instead of having to take square roots, we have to take cube roots, which is, you know, a little different. Really not much harder, but less familiar, maybe. Okay, and now we need to check. We've already checked x plus 5. We know that's not factorable. X minus 3, again, is linear, so we know that's not factorable. Hi, Carrie. You're welcome. Pedro, for you, sir. It's an after classer. And then that leaves this last part, this trinomial piece. I will tell you guys right now that if we're following the directions for our factoring diagram the flow chart we just built, when you do a sum or difference of two cubes, that last part's not going to be factorable either. So you can get away with just stopping here. Okay. The one place where you could have gotten into trouble is if you had two sum or differences of cubes that were also a difference of two squares, and you do the cubes part before you do the difference of squares part. If you do it in that order, you can run into something that is a trinomial that is factorable there. But as long as we're following the outline that I gave you, I don't think that can happen. I haven't proven that. I haven't sat down and thought about it hard enough to know if that's for sure true, but I designed it to mitigate that instance anyways, or prevent that thing from happening. How are we feeling? Let's do some more, right? This is not trivial by any means, right? It's new, but I'm hoping that having the outline really kind of helps keep track of where you're at and where we're going. So you always have the directions of kind of what to do next before when you can stop, right? And to some extent, just like getting some experience really kind of helps. Ooh. Oh, excuse me, I'm so sleepy. All right, first thing we do is we look for greatest common factor. Good. What is it? There isn't one, right? 65 isn't divisible by 8, or really, the fact that it's odd should be enough because 2 is just, or 8 is a power of 2. So we know that if 2 doesn't divide 65, then it doesn't matter. None of the other factors of 8 will divide 65 either because they're all just powers of 2. Okay, so got 3 terms. Is this in the quadratic form? Definitely. The leading coefficient here, though, is 8. So if we're going to be able to factor this, we're going to have to do the full version of the factoring. So we're going to need the 2 numbers that multiply to give us 8 times 8. And add to give us negative 65. Does anybody see the 2 numbers that do that? Should be easy to see them. Maybe it's too easy. 64 and 1, right? But it needs to be negative 65, so negative 1 and negative 64. Everybody agree with that? Good job, Gabby. Now remember, when we have to do the full version, though, that doesn't take us straight to our answer, right? The negative 1 and the negative 64 we use to break up that middle term into 2 pieces. And it doesn't really matter which order you put them, whether you did the negative 64 first or the negative 1 first, it doesn't matter. And then we do factor by grouping here. The first group we can take out a greatest common factor of x cubed. Very good. That leaves us with 8x cubed minus 1. The second group we can take out a greatest common factor of 8. I would do negative 8 though, because typically we want the leading coefficient inside the term to be positive. So let's do negative 8 instead of positive 8. That'll just cause the signs to switch there when we take the negative out, right? So the one that was negative becomes positive, and the one that was positive just becomes negative. So this is factorable, right? Because this is the same. Everybody agree? Okay, so we'll continue and finish up the factor by grouping here. So far, so good. Manuel, you're making some faces. You're okay or no? Okay. Now we need to check each one of these through the 2 term. So we'll start with the 8x cubed minus 1. Is that a difference of 2 squares? Definitely not, because the exponent is odd. Is it a sum or difference of 2 cubes? It is. So how do I rewrite 8x cubed as something to the 3rd power? So 2x to the 3rd is 8x cubed. Everybody agree with that? How do I rewrite 1 as something to the 3rd power? Just 1, right? Because 1 times 1 times 1 is just still 1. Okay. And then we can do similarly over here. That one was probably easier to see that it was a difference of 2 cubes, would be my suspicion. Okay? So again, our difference of two cubes factoring pattern, I'll write down here on the side so that when you're going back to look at your notes, it doesn't feel like magic where that came from. And I'm going to put a little subscript since we have two differences of two cubes so that we're not confused about like what's A and B. So the first one I'm going to use A1 and B1. The second one I'll use A2 and B2 just to kind of keep things straight. Is that okay with everybody? All right. So I have A minus B, so 2x minus 1, times A squared, so 2x squared, which would be 2x times 2x, which is 4x squared, plus, oops, there's no 2 there, plus A times B, so 2x, plus B squared, so 1 squared is 1. And then my next piece, I'm going to have A minus B, so x minus 2, and then A squared, so x squared, plus A times B, so that's 2x, plus B squared, so that's 4. If I check through, again, linear, the result of a sum or difference of cubes, so that's not factorable. Linear, the result of a sum or difference of cubes, that's not factorable. So we are donezo on that one. Peter? Of course. So this is our final answer. Okay. Let's just do one more, and we'll call it good. This is a lot of stuff to kind of pound through today. So you probably need some time to just relax and process here. We'll do one more, and then we'll be done. Sound good? What letter am I on? E. Thank you. X to the 8th minus 1. Okay, where do I start? Okay, is there one? No. Okay. Next up, what do I do next? Number of terms. How many terms is this? 2. Okay. What's the first thing I check for 2 terms? Difference of 2 squares. Great. Is this a difference of 2 squares? Yes. Hi. Thanks. Okay. So how do I rewrite x to the 8th as something squared? Good. X to the 4th squared. Now how do I rewrite 1 as something squared? 1. So this can become x to the 4th minus 1 and x to the 4th plus 1. So far, so good. Okay, what do I do after this? Okay. Good, so I have to check each of these factors. So x to the 4th minus 1 has 2 terms, right? What's the first thing I check in 2 terms? Difference of 2 squares. Is x to the 4th minus 1 a difference of 2 squares? What is it? You would just want to do this and go straight to it. I'm okay doing that. I think at this point we kind of get the idea. We've done a couple like that where I've gone and showed that it was a square before doing that. How about x to the 4th plus 1? Is that a difference of 2 squares? No. Why not? Good, because it's a sum. Next, we would check, is it a sum or difference of 2 cubes? Definitely can't be because 4 isn't a multiple of 3. The exponent isn't a multiple of 3. So that one we can't do anything more with. So that part is done. But we then have to check x squared minus 1 and x squared plus 1. They're both two terms. We start our two-term branch with difference of two squares. X squared minus 1, is that a difference of two squares? Yes. And the x squared plus 2, or I'm sorry, x squared plus 1, is that a difference of two squares? No. Is it a sum or difference of two cubes? No. So that one's done also. And since x minus 1 and x plus 1 are both linear, we know those are finished. So there's our final answer. Okay with that? Okay. So again, what we did today, not that much different than what we were doing first semester, right? Pretty similar. We can see now why we spent so much time first semester talking about factoring, because it comes up again and again, over and over and over again, and almost everything we just did today was fundamentally based on what we did first semester. We'll continue to kind of build on this. Today or tonight for your homework, I have 6 factoring problems. These are all two-term factoring problems, so we're just going to work on using part of the tree, or that flow chart. We'll do some more practice and build some more from this tomorrow, but as you guys have noticed at this point, basically after any branch you go down, you end up using the two-term branch afterwards. So we're going to start there and just work on factoring some of these pieces that are, involving the two-term branch. And we'll continue to add some more practice on in the next coming days. So we'll take a couple of days kind of on this topic. But from here, where we're at, we're not going to get new content here in terms of factoring for a while. We'll talk about how we can use this factoring technique to solve in these situations, but we won't add on any new factoring technique to this for a while. We'll stay here and practice this for a couple of lessons before we move on and add in the next set of factoring techniques that we can use to fill in some of those blanks in our table. Like, what do we do if we have more than 4 terms? And what do we do if, like, I have something that's, that's 3 terms and not in the quadratic form, or 4 terms and it wasn't factorable by grouping? Is there even anything I can do in those situations? And you're going to find that yes, there is, that we can do, do some. There are some other things that we can try. But again, I want to be upfront and honest with you. Factoring any polynomial is not, while it's possible, there's not always a good procedure, an easy way to do it. Sometimes it turns into just like brute force. Now, we're not going to encounter any of those situations in this course. Everything that I'm going to give you is something that's doable using one of the techniques I give you. But I don't want you to get the misconception that, like, factoring a polynomial in general is an easy problem, because it's not. There isn't, like, just a closed form procedure you could write to program a computer to do it. It would turn into just like brute forcing, where if you had like 100-term polynomial, it's going to take the computer like an hour to do that, because it's going to have to just like, do a lot of guessing and checking, ostensibly. Particularly if you wanted to factor it over like irrational numbers or complex numbers, then it's going to be a real bear. Anyways, though, this is where we're going to stop. So these 6 problems are your homework. We have, 15, 20 minutes left. What do we finish at 10:35? So almost 20 minutes left. If you wanted to start on this, you could probably finish a good chunk of it before you have to go. So that much less you'd have to worry about tonight or tomorrow or next, Sunday afternoon, depending on how much you wanted to put things off. I recommend not putting it off till all one day, but makes for a pretty miserable Sunday if you have a week's worth of math homework to do, especially if you have a 3-class week. Yes, sir? I don't, but if you want to run to the bathroom, that would be fine. Say hi to Peter while you're there.
What? Sorry.
I said say hi to Peter while you're there.
I will.
He's been gone for a minute, that's why.
I saw him in the hallway.
Yeah. Yeah, I'm just mostly making jokes. Little subtweety, mostly jokes.